Invisible messengers from deep space constantly strike our planet. These are cosmic rays, mysterious high-energy particles born in the universe's most violent events. This journey through the 25 most enigmatic cosmic rays will reveal how they are rewriting the laws of physics. We will encounter a single particle with the energy of a pitched baseball and investigate whether an ancient Siberian explosion was caused by a speck of antimatter. What cosmic mystery most captures your imagination? That invisible rain of cosmic particles includes one so extraordinary it was named the "Oh my God" particle. On a routine October day in 1991, a cosmic ray detector in Utah recorded something that should not exist. A single subatomic particle, likely a proton, slammed into our atmosphere carrying kinetic energy equivalent to a baseball hurtling at 60 miles per hour. All that raw, destructive power was squeezed into a speck smaller than an atom. Think about the force needed to throw a baseball, then imagine that same energy packed into one tiny particle traveling at almost the speed of light. The sheer intensity of this event left physicists in a state of stunned disbelief, hence its unforgettable name. This discovery shattered expectations. According to a well-established limit in physics called the GZK cutoff, such a high-energy particle should not be able to travel across the vast emptiness of space. It should have collided with the faint afterglow of the Big Bang, the cosmic microwave background, and dissipated its energy long before it ever reached Earth. The "Oh my God" particle did the impossible, arriving with an energy that defied our understanding of the universe's rules. Its very existence points to cosmic accelerators of unimaginable power, engines in the void that we have yet to discover. Yet the story of cosmic rays is far more than a collection of record-breaking particles. To truly understand their origins, we must look at the entire population, mapping their energies like a vast celestial census. This map reveals a strange and crucial feature known as the ankle. Picture a graph plotting the number of cosmic rays against their energy. For the most common lower energy rays, the line slopes downward steeply. But at a specific, tremendously high energy point, that steep slope suddenly flattens out, creating a shape that vaguely resembles the curve of an ankle. This is not a minor statistical blip. It is a fundamental shift in the behavior of the universe's most energetic particles, a bend in the road that marks a profound transition. Scientists believe this ankle could be the point where we stop seeing cosmic rays from within our own Milky Way galaxy and start observing particles born in the terrifying depths of intergalactic space. Imagine you are listening to a crowd. The loudest voices nearby are easy to hear, but to catch the whispers from a distant city, you must filter out the local noise. The ankle may be that moment when the local galactic noise fades and the faint, powerful signals from far-off galaxies finally become clear. The debate, however, is fierce. One camp argues this is a change in the cosmic rays themselves, a sign that a new, more powerful type of accelerator takes over beyond this energy. Another theory suggests it is about the journey. Perhaps all ultra-high-energy particles come from extragalactic sources, but the lower-energy ones lose speed and change as they struggle through the tangled magnetic fields of our galaxy. The ankle, then, is the energy at which they finally break free and travel to us more directly. This single feature on a graph represents a frontier, the border between our galactic home and the vast, unknown cosmos beyond. But what happens when a cosmic ray does not just tickle a detector, but reshapes a landscape? In the early morning of June 30th, 1908, a remote Siberian forest near the Tunguska River became the stage for one of history's most violent and mysterious explosions. An immense fireball tore across the sky, followed by a shockwave that flattened over 800 square miles of ancient trees. The blast was heard hundreds of miles away, and its atmospheric effects were observed across Europe. For decades, the leading explanation pointed to the airburst of a comet or asteroid, a theory that neatly explains the devastation and the conspicuous absence of an impact crater. Yet, the sheer scale of the destruction and the peculiar nature of the event left room for a far more exotic possibility. A controversial hypothesis suggests the Tunguska event was not a rock from space, but a visitor made of pure energy, a massive chunk of antimatter. In this theory, a cosmic ray composed of antimatter, perhaps a fragment from a distant stellar cataclysm, journeyed across the cosmos only to meet its end in Earth's atmosphere. When antimatter encounters normal matter, they annihilate each other in a flash of energy, converting their entire mass into a tremendous explosion. This process would create a powerful airburst with no solid meteorite fragments left behind, perfectly matching the strange evidence on the ground. While the comet or asteroid theory remains the most widely accepted, the antimatter hypothesis forces us to confront a startling idea. The same invisible particles that quietly pass through us every day could, in an unimaginably rare and powerful form, wield the force of a nuclear bomb. Was Tunguska a cosmic accident, or was it a message written in fire, a testament to the raw power hidden within the simplest building blocks of our universe? For a brief, electrifying period, astronomers thought they had found the first true cosmic ray gun in the heavens. The target was a bizarre object known as Cygnus X3, a binary system where a dense neutron star or black hole slowly consumes its companion. In the 1970s and 80s, multiple research groups announced a stunning discovery. They reported detecting bursts of ultra-high-energy gamma rays and cosmic rays that seemed to arrive from this single point in the constellation Cygnus. This was the holy grail of cosmic ray science. For decades, these particles had seemed to rain down from everywhere and nowhere, their origins completely anonymous. To finally pin a cosmic ray to a specific object, a known celestial machine, would be a monumental breakthrough. It would prove that such binary systems were natural particle accelerators of almost incomprehensible power. The scientific community was thrown into a frenzy of excitement and intense scrutiny. The initial data was compelling, suggesting that Cygnus X3 was firing beams of particles directly at Earth with a rhythmic, clock-like precision tied to its orbital dance. But as more teams turned their instruments toward this cosmic suspect, the evidence began to unravel. The initial detections were incredibly difficult to reproduce. Other observatories, sometimes using more sensitive equipment, pointed at the same patch of sky and found nothing out of the ordinary. The rhythmic signals that seemed so clear to some appeared as mere statistical flukes to others. The controversy grew into one of the most debated episodes in modern astronomy. Was Cygnus X3 a revolutionary discovery, or was it a case of scientists seeing patterns in the noise, a cosmic mirage born from hope and the immense challenge of detecting these elusive particles? Over time, with more refined measurements and a cooler head for statistics, the consensus shifted. Cygnus X3 was largely acquitted of being a direct source of these particular cosmic rays. Yet its legacy is far from a simple failure. It stands as a classic cautionary tale about the perils and promises of hunting for the universe's most elusive signals. It taught physicists to be more rigorous, to demand near irrefutable proof before claiming a discovery, and it underscored just how difficult it is to trace a single, charged particle back across millions of light-years of magnetized space. The case of Cygnus X3 reminds us that the path to truth is often paved with false leads, each one sharpening our questions and guiding us closer to the real cosmic ray masters still hiding in the dark. While the ankle points us toward the distant universe, another cosmic landmark much closer to home holds a different kind of clue. Deep within the spectrum of common cosmic rays lies a subtle but critical bend known as the knee. Picture a highway filled with cars, most of them moving at a steady, predictable speed. Now, imagine that at a very specific high speed, the number of cars suddenly and dramatically plummets. That is the knee. It is a distinct point around 10 to the 15 electron volts where the abundant flow of cosmic rays suddenly drops off a cliff. For decades, this feature has been a central puzzle, a signpost that something fundamental changes in the origin or journey of these particles. Why does the universe's supply of these energetic messengers seem to run out at this specific energy? One compelling theory points to the limits of our own galaxy's power plants. Supernova remnants, the expanding shells of gas from exploded stars, are thought to be the primary accelerators for most cosmic rays we detect. These colossal shockwaves can sling particles to incredible speeds, but even they have a maximum output. The knee may represent that ultimate energy ceiling. It could be the point where a supernova's magnetic shockwave simply cannot push a proton any faster. Think of it like a carnival ride that can only spin so fast before it flings everyone off. The knee, in this view, is the natural speed limit for particles born within the Milky Way. Another explanation focuses not on acceleration but on escape. Our galaxy is not an empty void, it is laced with a tangled web of magnetic fields. These fields act like a cosmic maze, trapping lower energy particles and making them bounce around for thousands of years before they eventually leak out. But as particles gain more and more energy, they become harder for these magnetic fields to contain. The knee could be the energy threshold at which cosmic rays finally have enough power to break free from the galaxy's magnetic grasp. They stop being trapped residents and become swift travelers, escaping into intergalactic space so quickly that their numbers near Earth dwindle. So, is the knee a sign of a generator shutting down or a prison wall being breached? This single bend in a graph forces us to ask where the galactic environment ends and the particles themselves begin. It is a reminder that the cosmos is filled with invisible boundaries, each one dictating which messages from the void we are allowed to receive. This unexpected surplus of positrons presents a cosmic puzzle with profound implications. For decades, physicists understood that cosmic rays should contain a specific, tiny fraction of these antimatter particles. They are typically created when high-energy protons, the main component of cosmic rays, collide with interstellar gas, a process that produces them in predictable, limited numbers. But the data from advanced instruments like the PRMELA satellite and the MS-02 experiment on the International Space Station told a different story. They revealed a clear and growing excess of positrons at high energies, a surplus that defies conventional explanations. It is as if you were counting cars on a highway, expecting one red car for every 100 blue ones, but as you looked at faster and faster vehicles, you started seeing more and more red cars, eventually outnumbering the blue. This is not a minor statistical anomaly. It is a signal that something is fundamentally wrong with our standard model of cosmic ray propagation, or that an entirely new source is at work. The most thrilling possibility is that we are seeing the fingerprints of dark matter. Certain theoretical models propose that dark matter, the invisible substance that makes up most of the universe's mass, could be composed of weakly interacting massive particles, or WIMPs. If two of these particles were to collide, they could annihilate each other in a burst of pure energy, a process that would produce, among other things, a flood of electrons and positrons. This could perfectly explain the observed excess, turning a cosmic ray anomaly into the first direct evidence for the nature of dark matter. Yet, nature often offers more mundane, though no less spectacular, explanations. Another leading candidate is the pulsar, the rapidly spinning, magnetized core of a dead star. These celestial lighthouses whip charged particles around with such ferocity that they can create matter and antimatter out of the vacuum of space itself, potentially generating the exact positron surplus we detect. So we are left with a beautiful and frustrating dilemma. Is this positron excess the long-awaited signal from the dark universe, a whisper from the 85% of reality we cannot see? Or is it the spectacular but conventional exhaust from a nearby stellar corpse, The hunt for the answer continues, forcing us to look deeper into the data and further into the void to distinguish between a new chapter in physics and the breathtaking power of known cosmic engines. The mystery of the positron excess leads us to an even grander puzzle, the origin of the universe's ultimate bullets. These are the ultra-high-energy cosmic rays, particles with energies so immense they defy comprehension. Yet for all their power, they arrive at our detectors as cosmic ghosts, their true homes hidden from view. The core of the problem lies in their electric charge. Because most of these particles are protons, which carry a positive charge, they do not travel in straight lines. Instead, they are whipped and twisted by the invisible magnetic fields that fill the voids between galaxies. A proton born in a cataclysm 100 million light-years away does not point back to its source like an arrow. Its path is a tangled, spiraling mess, a chaotic journey that erases its starting point. It is like trying to trace a single leaf caught in a hurricane back to the exact tree it fell from. The most energetic particle ever detected could have begun its life in a distant, brilliant quasar, but by the time it reaches us, its trajectory is a useless clue. This is the fundamental frustration of cosmic ray astronomy. We are receiving the most powerful messages the universe can send, but they arrive with the return address torn off. To even begin solving this, scientists built the largest scientific instruments on Earth. The Pierre Auger Observatory in Argentina covers an area of over 1,000 square miles, an array of 1,600 water tanks that watch for the faint flashes of light created when a cosmic ray shreds the atmosphere above. Its goal is not just to measure the energy of these particles, but to map their arrival directions across the entire sky. The results of this monumental effort are both tantalizing and deeply puzzling. The map is not perfectly smooth. It shows a subtle but statistically significant hotspot, a region of the sky where these ultra-high-energy particles seem to arrive more frequently. This is a crucial clue, suggesting that their sources are not distributed evenly throughout the cosmos. Yet this hotspot is not a single bright point. It is a broad, fuzzy patch, and it does not line up perfectly with any single known class of celestial object. The accelerators responsible must be extraordinarily powerful and relatively nearby, within a few 100 million light-years, or the particles would have been destroyed by the cosmic microwave background. But what are they? Active galactic nuclei, with their supermassive black holes devouring matter, are prime suspects. So are the chaotic environments of galaxy collisions, where immense shockwaves could accelerate particles to these unbelievable energies. The map gives us a blurry photograph of the culprit, but not a name. We are left staring at the sky, knowing that unimaginable engines are firing these particles at us, yet we still cannot point to them with certainty. The hunt continues, a cosmic detective story where the clues are written in paths of twisted light. This subtle lopsidedness in the cosmic rain is known as anisotropy. It means the universe is not spraying these particles at us with perfect, uniform randomness. Instead, there is a slight but statistically significant preference, a gentle current in the vast ocean of space. One of the most compelling of these currents flows from the direction of the Vela constellation. This is not a single, sharp point of light, but a broad, diffuse excess, a region of the sky from which just a few more cosmic rays seem to arrive than from other areas. Finding this signal is like trying to hear a single soft whisper in a roaring stadium. It requires instruments that can collect billions of events over many years, patiently building up a map until the faint pattern emerges from the chaos. The immediate and most logical suspect is the Vela supernova remnant itself. Located a mere 800 light-years away, it is one of the closest and most active stellar corpses we know. This expanding shell of gas is the aftermath of a star that exploded in a cataclysm witnessed on Earth roughly 11,000 years ago. Its powerful shockwaves are exactly the kind of natural particle accelerator thought to produce the cosmic rays that fill our galaxy. The anisotropy seems to point a finger directly at this nearby cosmic engine, yet the case is far from closed. The signal from Vela is broad and smeared, not a precise beam. This blurring is the work of those same galactic magnetic fields that scramble the paths of ultra-high-energy particles. Even the cosmic rays from a source as relatively close as Vela are twisted and bent on their journey to us, their paths corrupted so they appear to come from a wide swath of sky rather than a single point. This creates a profound challenge. We have a hotspot and we have a prime suspect, but we cannot prove they are directly connected beyond a reasonable doubt. It is like having a crime map showing a neighborhood with elevated activity and a known troublemaker living right in the middle of it. The correlation is strong, but is it causation? Could other, fainter sources in that same general direction be contributing to the flow? The Vela anisotropy is a tantalizing clue, a hint that we are on the verge of truly connecting specific cosmic rays to their birthplaces. It proves that the cosmic fog is not impenetrable, that with enough patience and precision, we can begin to see the outlines of the giants hiding within it. But the influence of cosmic rays may reach far beyond our own galaxy, touching the very elements that make up the universe. There is a strange and persistent mismatch in our cosmic ledger, known as the cosmological lithium problem. Our most successful model of the early universe, Big Bang nucleosynthesis, predicts with stunning accuracy how much hydrogen and helium was forged in the first few minutes after the Big Bang. Yet for the third lightest element, lithium, the math does not add up. The models predict about 3 times more lithium-7 than we actually observe in the oldest stars in our galaxy. So where did all the lithium go? One compelling suspect is the constant, invisible rain of cosmic rays. The theory suggests that over billions of years, these high-energy particles have been acting as elemental vandals. As they streak through clouds of interstellar gas, they can smash into the fragile nuclei of that primordial lithium, breaking them apart into smaller atoms like helium. This process, called spallation, is a nuclear demolition derby. Imagine a beautifully arranged tower of blocks representing the lithium atom. A cosmic ray, like a wildly thrown ball, smashes into it, scattering the pieces and leaving only rubble behind. This slow, relentless destruction could account for the missing lithium, painting cosmic rays not just as messengers, but as active shapers of the chemical cosmos. Of course, other explanations exist, perhaps involving novel physics in the early universe or complex stellar processes. Yet the cosmic ray hypothesis holds a powerful appeal. It suggests that the answers to our grandest cosmological questions are not just found in the first moments of time, but are being written and rewritten every day by the silent, energetic traffic flowing through the voids of space. One of the most peculiar tools for studying the sky involves looking at an absence. Our own moon, as it journeys across the heavens, casts a shadow in cosmic rays. This is not a shadow of darkness, but a shadow of silence, a faint dip in the constant rain of particles detected on Earth. As the moon passes in front of a source of cosmic rays, it blocks them, creating a void in the data that should precisely match the moon's size and position. This cosmic ray shadow is a fundamental test for our detectors. If an observatory can clearly see this sharp, moon-shaped hole in the particle rain, it proves the instrument has excellent angular resolution, meaning it can pinpoint the direction a cosmic ray came from with incredible accuracy. It is the ultimate calibration tool etched into the sky by a celestial body, but sometimes this shadow does not behave as expected. Scientists have observed it appearing smeared, distorted, or even shifted slightly away from the moon's true position. This strange warping is not a flaw in the detectors, it is a message. The culprit is the interplanetary magnetic field, the vast, invisible magnetic web woven by the sun and stretched throughout our solar system. Charged cosmic ray particles do not travel in straight lines. They are deflected by these magnetic fields, their paths bent into gentle curves. When a cosmic ray that should have been blocked by the moon is nudged by a magnetic field, it can be steered around the obstacle and still reach Earth, effectively filling in the shadow. Conversely, particles that should have reached us can be deflected away, making the shadow appear to shift. By carefully measuring the exact amount of distortion in the moon's shadow, physicists can reverse engineer the strength and structure of these invisible magnetic forces. A sharp, clear shadow tells us the magnetic fields are calm. A blurred and shifted one reveals a turbulent, magnetically stormy environment between the planets. So every time the moon passes overhead, it does more than just reflect light. It casts a shadow made of nothing, a ghostly silhouette that lets us map the invisible architecture of our own solar system. Sometimes the most important discoveries are the ones we initially miss. Just 500 light-years away, a cosmic powerhouse was hiding in plain sight for decades. This is the Geminga pulsar, a dense neutron star spinning rapidly in the constellation Gemini. It was first noticed not by its light or its radio waves, but by a faint glow of gamma rays detected by a satellite in the 1970s. For years, its nature remained a mystery, earning it the name Geminga, which in the local Italian dialect of Milan loosely means "it's not there." We eventually learned that Geminga is very much there, a stellar corpse so active it creates a massive bubble of high-energy particles around itself. As the debate over the positron excess heated up, all eyes turned to this nearby, energetic object. Could this be the local factory churning out the extra antimatter we were detecting? Geminga seemed like a perfect culprit. Its powerful magnetic field and rapid spin act like a colossal natural particle accelerator, capable of generating immense numbers of electrons and positrons. These particles would then stream out into space, potentially flooding our corner of the galaxy and explaining the mysterious surplus, but the evidence was not so straightforward. The key question was one of delivery. Could the positrons created by Geminga actually travel the 500 light-years to Earth? The space between stars is not empty. It is filled with a turbulent sea of magnetic fields that scatter and slow down charged particles. Some scientists argued that by the time Geminga's positrons made the journey, they would have lost too much energy and become too diffused to account for the sharp signal we observe. The debate centered on a faint, extended halo of gamma-ray light surrounding Geminga, recently mapped in exquisite detail. This halo is the telltale glow created when the pulsar's high-energy electrons and positrons interact with starlight. The size and brightness of this halo suggest that the particles are indeed being confined close to the pulsar, not streaming freely across the galaxy. It is as if we found a factory producing exactly the product we were looking for, but then discovered its shipping department is too inefficient to get the goods to our doorstep. So is Geminga the source of the positron excess, or just a spectacular red herring? This single pulsar forces us to ask profound questions about how particles travel through the galactic medium. Its enigmatic nature reminds us that even when we find a likely suspect, the universe has a way of complicating the story, blurring the line between a solution and a deeper mystery. These cosmic hotspots are the closest we have come to identifying the universe's ultimate particle accelerators. The data points toward a lopsided sky where certain regions appear to glow faintly with an excess of the most energetic particles. The most significant of these, detected by the colossal Pierre Auger Observatory, is a broad patch in the sky not far from the constellation Centaurus. This is not a single brilliant point, but a diffuse glow, a celestial neighborhood that seems to produce more than its fair share of cosmic bullets. The immediate and most thrilling suspects are active galactic nuclei, the monstrous hearts of distant galaxies. These are supermassive black holes weighing billions of times our sun's mass that are actively feeding on surrounding gas and dust. As matter spirals into the abyss, it heats up to incredible temperatures and can launch jets of plasma and radiation across millions of light-years. These jets are prime candidates for the engines that can accelerate protons to such unbelievable energies. The chaotic environment is a perfect natural version of our most powerful particle colliders, but on a scale we can barely comprehend. Another potential source lies in the violence of starburst galaxies. These are galaxies undergoing a frenzy of star formation, where thousands of stars are born in a relatively short cosmic time. This stellar baby boom leads to a corresponding surge in supernova explosions, each one a powerful shockwave that could, in concert, create a vast accelerator capable of reaching ultra-high energy thresholds. The correlation is tantalizing, but it is not yet proof. The primary challenge is statistics. Ultra-high energy cosmic rays are incredibly rare, with perhaps just one particle per square kilometer per century arriving at the top of our atmosphere. Building a map requires years, sometimes decades, of patient data collection from a detector the size of a small country. Even with the Auger Observatory's immense scale, the number of these extreme events is still small. The hotspot we see is real, but it is fuzzy, and it overlaps with several potential source candidates. We cannot yet point to a single galaxy and declare it guilty beyond a reasonable doubt. It is like hearing a few loud shouts from a specific city block, but not being able to pinpoint which house they came from. The excitement, however, is palpable. Each new ultra-high energy event that arrives from that direction sharpens the image, adding one more day to point to a map we are only just beginning to draw. These hotspots are not just points on a chart, they are targets guiding our telescopes toward the cosmic monsters that have been shooting at us all along. The very identity of a cosmic ray holds the key to its origin. As we climb the energy ladder toward the ankle, the particles themselves begin to change. At lower energies, the cosmic ray population is a rich mix of elements, including heavy nuclei like iron, carbon, and oxygen. It is as if a cosmic foundry is spewing out the entire periodic table. These heavier particles carry more mass and charge, making them easier for our galaxy's magnetic fields to trap and accelerate. Their presence points strongly to local sources, like supernova remnants within our own Milky Way, where the debris of exploded stars provides the raw material. But as we approach the mysterious ankle, the composition appears to shift. The mix of particles seems to lighten, becoming dominated by lighter nuclei, primarily single protons. This transition is a profound clue. A proton, with its single positive charge, is far more susceptible to the pull and twist of magnetic fields than a heavy iron nucleus. If the highest energy cosmic rays are indeed protons, it helps explain why their paths are so scrambled and their sources so frustratingly anonymous. They are the ultimate cosmic drifters, unable to point back home. Why does the mix change? The answer may lie in the limits of acceleration. Perhaps the galactic accelerators that work so well on heavy nuclei simply cannot push the lighter, more slippery protons to energies beyond the ankle. Or, more intriguingly, it could be a sign that we are crossing a cosmic border. The heavy nuclei from our galaxy cannot travel vast intergalactic distances without being torn apart. A lone proton, however, is a hardy traveler capable of surviving a journey of hundreds of millions of light years. So the shift in composition at the ankle might be the moment we stop seeing the local galactic debris and start observing the pure, lightweight messengers from far-off galaxies. Decoding this elemental mix is like reading the passport of each cosmic ray, revealing not just its energy, but its journey and its birthplace. The universe's most violent detonations may be the very engines firing cosmic bullets at our planet. Gamma-ray bursts are the single most powerful explosions known to exist, brief flashes of light that can outshine entire galaxies. In a matter of seconds, a single burst can release more energy than our Sun will emit over its entire 10 billion-year lifetime. The leading theory suggests these cataclysms are the birth cries of black holes, either from the collapse of a hypermassive star or the merger of two dense neutron stars. In either scenario, the newborn black hole fires off two narrow, opposing jets of plasma and radiation at nearly the speed of light. It is within these focused beams of pure fury that physicists believe a special kind of alchemy occurs. As different shells of material within the jet catch up to one another and violently collide, they create what are known as internal shocks. These are not gentle ripples, but titanic, supersonic crashes that could act as the universe's most efficient particle accelerators. Within this chaotic maelstrom, protons and atomic nuclei could be whipped to velocities approaching the speed of light, gaining the staggering energies we detect as ultra-high-energy cosmic rays. The sheer power of a gamma-ray burst provides more than enough raw force to create even the legendary "oh my god" particle. Yet, proving this connection is one of the greatest challenges in modern astrophysics. A cosmic ray alone is not enough, its path too scrambled by magnetic fields to trace back with certainty to a brief, fleeting flash that may have faded eons ago. The hunt requires a different kind of messenger, one that travels completely unaffected by magnetic fields and points directly back to its source. This is where the ghostly neutrino becomes essential. If protons are being accelerated within a gamma-ray burst, they should also interact with the intense radiation field of the jet itself, producing a cascade of secondary particles, including high-energy neutrinos. These nearly massless particles, so elusive they can pass through a light year of lead without stopping, would travel in a perfect straight line from the burst directly to our detectors. Finding a neutrino that arrives at Earth at the exact same time and from the exact same direction as a gamma-ray burst would be the undeniable smoking gun. It would be the cosmic equivalent of finding a shell casing at a crime scene that perfectly matches the gun. Observatories deep under the Antarctic ice, like Ice Cube, are constantly watching the skies for these faint whispers, waiting for that one perfect coincidence that would solve the mystery. So far, the definitive link has remained elusive, with no strong correlation found between neutrino events and observed gamma-ray bursts. This absence is itself a profound piece of the puzzle, forcing theorists to refine their models. Perhaps the conditions inside the jets are not quite right for efficient neutrino production, or maybe these bursts are not the dominant source of the very highest energy cosmic rays after all. The search continues, a high-stakes race to catch two different signals from the same unimaginable explosion, a quest to prove that the universe's brightest flashes are also its most powerful hidden guns. These silent messengers do more than just travel, they actively shape the cosmos they pass through. We have been thinking of cosmic rays as passive signposts, but they are in fact dynamic forces, their immense energy sculpting the very galaxies they call home. Inside a galaxy like our Milky Way, these high-energy particles create a form of subtle but persistent pressure. This is not a physical push like the wind, but a radiation pressure, an invisible force exerted by their sheer energetic motion. In regions where stars are forming at a frantic pace, supernova explosions and young, massive stars fill space with a torrent of cosmic rays. This builds up a tremendous pressure that can actually drive powerful outflows, vast rivers of gas streaming out of the galaxy itself. These are galactic winds, and they are cosmic escape valves. They carry away enormous amounts of raw material, the very gas and dust that would otherwise collapse to form new stars. This process, known as cosmic ray feedback, acts as a cosmic thermostat for star formation. It prevents a galaxy from burning through its fuel too quickly in a single, explosive burst of stellar birth. Without this regulating force, a galaxy might blaze with light for a short time before sputtering out, its star-forming gas exhausted. Cosmic rays provide the gentle, persistent pressure that helps a galaxy live a long and stable life, ensuring it forms stars at a sustainable rate over billions of years. Their influence reaches even into the structure of the space between stars. The interstellar medium is not a uniform void. It is a foamy, chaotic sea of hot gas, cold clouds, and magnetic fields. Cosmic rays, with their ability to heat this gas and amplify magnetic fields, help stir this cosmic soup. They can prevent giant gas clouds from collapsing prematurely, or conversely, help trigger the final push that leads to a new star's ignition. So the next time you look at the serene band of the Milky Way, remember it is not a static painting. It is a dynamic ecosystem, its evolution guided in part by the relentless, invisible rain of particles from its own violent heart. But the cosmic rays we have encountered so far are not the only messengers in the void. A far gentler yet equally mysterious population flows through our solar system, known as anomalous cosmic rays. These are not the ultra-high-energy bullets from distant galaxies, but a unique local breed of particles with a very strange origin story. Their journey begins in the calm darkness between the stars with neutral atoms. Imagine a lone atom of hydrogen or helium, completely untouched, drifting for eons in the interstellar void. It carries no electric charge, making it invisible to magnetic fields, allowing it to glide unimpeded through space. Eventually, one of these neutral wanderers drifts into our solar system. As it approaches the Sun, it is bombarded by solar ultraviolet light, or the solar wind itself. This interaction strips an electron from the atom, giving it a positive electric charge in a flash of transformation. Suddenly, this once neutral drifter is no longer a ghost. It is now a charged particle, a puppet of the Sun's magnetic influence. The solar wind, that constant stream of charged particles flowing from the Sun, immediately grabs hold of this newly created ion and flings it outward, accelerating it on a journey to the very edge of our solar system. Its destination is the termination shock, the turbulent boundary where the solar wind slams into the interstellar medium and abruptly slows down from supersonic to subsonic speeds. This colossal shockwave acts as a natural particle accelerator, giving these interstellar immigrants one final, powerful kick. They are energized and flung back inward toward the inner solar system, where we can detect them as anomalous cosmic rays. Their composition is the key clue. They are not the usual mix of elements we see in galactic cosmic rays. Instead, they are overwhelmingly made of certain elements like helium, nitrogen, oxygen, and neon, materials that are common in the nearby interstellar cloud but are difficult to ionize. This specific fingerprint points directly to their origin as former neutral atoms. By studying these anomalous cosmic rays, we are not looking out at distant galaxies. We are taking a core sample of our local interstellar neighborhood. They are the only sample of material from beyond the Sun's influence that we can directly collect and analyze. Their very existence and properties tell a vivid story about the boundary of our solar system, the nature of the space just outside it, and the constant, quiet exchange of matter happening at the edges of the Sun's domain. They are a reminder that our solar system is not a sealed fortress, but a porous entity, continuously breathing in the raw material of the galaxy. The same particles that can shatter atoms might also shape our planet's weather. A provocative and fiercely debated theory suggests that cosmic rays are not just celestial visitors, but active players in Earth's climate, their influence felt in the very clouds that drift across our sky. The proposed mechanism is elegant in its simplicity, as a cosmic ray, typically a high-energy proton, smashes into the upper atmosphere. It shatters air molecules, creating a cascade of secondary particles and freeing electrons in a process called ionization. These newly freed electrons can act as microscopic anchors, attracting clusters of water vapor and trace gases like sulfuric acid. These clusters, in theory, can grow into stable cloud condensation nuclei, the tiny specks upon which water droplets form. More cosmic rays would mean more ionization, more potential nuclei, and ultimately more clouds. And since clouds reflect sunlight back into space, an increase in global cloud cover could lead to a significant cooling of the planet. This idea positions the cosmos as a grand climate regulator, where the ebb and flow of galactic cosmic rays, modulated by the Sun's magnetic activity, could drive long-term temperature changes. When the Sun is active, its strengthened magnetic field shields Earth from more cosmic rays, leading to fewer clouds and a warmer world. When the Sun is quiet, the cosmic ray flux increases, seeding more clouds and cooling the climate. It is a compelling narrative that connects the rhythms of our star to the weather outside our window. Yet, the scientific evidence for this hypothesis is a battleground. Proponents point to compelling correlations, like the striking overlap between periods of low solar activity, high cosmic ray counts, and cooler temperatures in Earth's historical record. Laboratory experiments have also shown that ionization can indeed enhance the formation of molecular clusters under controlled conditions. However, correlation is not causation, and this is where the theory faces its greatest challenges. The leap from a microscopic cluster in a lab chamber to a planet-spanning blanket of clouds is enormous. The atmosphere is a chaotic, complex system with countless variables. Critics argue that the effect of cosmic rays is simply too small to compete with the dominant processes of cloud formation, which are driven by far more abundant natural aerosols like sea salt and dust. Satellite data has so far failed to show a strong, consistent link between cosmic ray flux and global cloud cover. The signal, if it exists at all, appears weak and often disappears when other factors are considered. The controversy remains one of the most enigmatic in modern science, a beautiful idea that is perpetually on the verge of being either proven or discarded. It forces us to ask a profound question: is our climate a closed system, dictated solely by terrestrial forces and human activity, or is it an open book, its pages subtly turned by the invisible hand of the galaxy? Rising from the heart of our galaxy are two colossal structures that defy easy explanation. Known as the Fermi bubbles, these vast lobes of gamma-ray light balloon outward from the Milky Way's core, stretching for 25,000 light-years above and below the galactic plane. If our eyes could see in gamma rays, this hourglass shape would dominate the entire night sky, a silent testament to some ancient cataclysm. These are not bubbles of gas in the ordinary sense. They are immense cosmic reservoirs, likely filled to bursting with high-energy particles and powerful magnetic fields. When fast-moving electrons spiral through magnetic fields, they give off a specific type of radiation called synchrotron emission, and the smooth, sharp-edged glow of the Fermi bubbles points to this very process. But electrons are not traveling alone. The same turbulent environment that accelerates electrons to near light speed is also a perfect factory for their heavier counterparts, protons and atomic nuclei. This means the bubbles are almost certainly brimming with cosmic rays, trapped within these magnetic structures and slowly radiating away their immense energy. The sheer scale of these bubbles reveals a power source of almost unimaginable force, an eruption that must have rocked the entire galaxy. So what event could have created such monumental structures? The prime suspect is our own galaxy's central supermassive black hole, Sagittarius, a star. While it is quiet today, there is compelling evidence that it was once a voracious engine of destruction. One leading theory suggests that in the distant past, a massive cloud of gas or a star drifted too close and was torn apart by the black hole's immense gravity. As this material spiraled into the accretion disk, it could have triggered a violent outburst, launching twin jets of ultra-fast plasma and radiation directly perpendicular to the galactic disk. These jets would have punched through the surrounding gas, inflating the massive bubbles we see today and filling them with accelerated particles. It would have been a brief but spectacularly violent event, a single roar from the galactic center that echoed for millennia. Another compelling hypothesis points not to the black hole, but to a frenzy of stellar birth and death. The galactic center is a crowded, dynamic place, and it may have experienced a period of intense star formation, a starburst. In such an environment, thousands of massive stars would be born only to die a few million years later in simultaneous supernova explosions. The combined shock waves from all these blasts could have blown a gigantic collective bubble, driving a super wind that carved out the structures and loaded them with cosmic rays. This would be a more democratic, distributed explosion rather than a single-point source. The debate between these two ideas, a single monstrous eruption versus a coordinated chorus of stellar deaths, lies at the heart of the mystery. Were the Fermi bubbles forged in the brief, terrifying fury of a feeding black hole, or were they sculpted by the sustained, brilliant fire of a million dying stars? These silent, glowing forms hold the answer, a frozen record of a time when the center of our galaxy was a far more violent and active place. They remind us that even our seemingly calm Milky Way has a turbulent and explosive history, written in the language of light and trapped cosmic rays. The universe erects invisible barriers to keep its most powerful secrets hidden. One of the most formidable is the Greisen-Zatzepin-Kuzmin, or GZK, cutoff. This is not a physical wall, but a fundamental law of cosmic travel for the most energetic particles. According to this limit, any proton with an energy exceeding 10 to the 20th electron volts should not be able to journey across intergalactic space. The reason lies in the faint, cold glow that fills the entire cosmos, the cosmic microwave background radiation. This is the cooled remnant of the Big Bang's fireball, a bath of photons that has been traveling for over 13 billion years. For an ultra-high-energy proton, this serene background is a minefield. Each photon, though weak, appears as a high-energy blast of radiation to a proton moving at almost the speed of light. When they collide, the reaction creates a new particle, a pion, which drains the proton's energy. Over a distance of just a few 100 million light-years, this constant bombardment should slow these cosmic bullets down, draining them below the GZK energy threshold. They should never reach Earth, and yet they do. Our detectors have recorded multiple particles with energies that blatantly surpass this theoretical limit. It is as if a marathon runner, told they must run through a field of thick, clinging mud, somehow arrives at the finish line not only dry but faster than ever. This contradiction presents a stark choice, a fork in the road of our understanding. One possibility is that these particles are not cosmic marathoners at all, but local sprinters. Their sources must be extraordinarily close on a cosmic scale, within our own galactic neighborhood or a nearby galaxy cluster. If they only have to travel a short distance, they might not have time to interact with enough background photons to slow down significantly. This would mean that the most powerful particle accelerators in the universe are not in distant, ancient galaxies, but practically in our own backyard. We would need to search for a monstrous, hidden engine within a few 100 million light-years capable of these feats. The other, far more radical possibility is that our understanding of physics itself is incomplete at these extreme energies. The laws that govern particle interactions, tested so precisely in our terrestrial colliders, might break down when pushed to such absolute limits. Perhaps these ultra-high-energy protons interact with the cosmic background in a way we have not predicted, or maybe they are not protons at all, but something more exotic, like a new type of stable, massive particle that is immune to the GZK process. Each detection of a super GZK particle is a direct challenge, a data point that defies a well-established pillar of modern physics. Are we missing a key piece of the cosmic map, or are we reading the rules of the universe wrong? The answer will rewrite not just the story of cosmic rays, but our most fundamental theories of reality. The silent annihilation of dark matter could be flooding our galaxy with cosmic rays. Deep in the void, the very substance that holds galaxies together might be destroying itself, and the only trace we can find is in the high-energy particles that strike our detectors. This idea centers on a hypothetical particle known as a WIMP, a weakly interacting massive particle. These are thought to be their own antimatter counterparts, meaning that when two WIMP collide, they would annihilate each other in a flash of pure energy. That energy would then condense into a cascade of standard particles, including protons, electrons, and their antimatter twins, positrons. It is a ghostly process happening all around us in the vast halo of dark matter that envelops our Milky Way, yet it is completely invisible to our eyes. The resulting cosmic rays would carry a unique signature, a specific pattern in their energy and type that could, in theory, be separated from the chaotic background of astrophysical sources. The mysterious positron excess we detect could be the direct fallout of this continuous, invisible war occurring in the dark. It would be the first tangible evidence for a substance that makes up 85% of the universe's matter. The hunt for this signal is a meticulous process of elimination. Scientists use incredibly sensitive instruments, like the MS-02 spectrometer on the International Space Station, to measure the cosmic ray flux with unprecedented precision. They are not just counting particles, they are mapping the detailed energy spectrum of positrons, looking for a sharp, distinctive peak or a specific cutoff that would be the smoking gun for dark matter. The challenge is that pulsars, the spinning remnants of dead stars, can produce an almost identical signal. Both dark matter annihilation and a pulsar's furious magnetic fields create floods of positrons. Telling them apart is like trying to identify a single instrument in a roaring symphony. One key difference might lie in the map of the sky. A signal from dark matter annihilation should be smooth and diffuse, spread across the entire galactic halo because the dark matter is everywhere. A signal from a single nearby pulsar, however, might appear as a bright, localized point. Yet even this clue is blurred by the tangled magnetic fields of the galaxy, which scatter the particles and smear their origins. The search continues, a high-stakes detective story where the suspect is the universe itself. Are we on the verge of a discovery that will redefine physics, or are we simply hearing the familiar, if spectacular, roar of known cosmic engines? The answer is written in the silent rain of particles, waiting for us to decode its deepest secret. Sometimes the most powerful cosmic ray might not be a single particle at all. A speculative but fascinating idea suggests that what we record as a single, impossibly energetic event could actually be a coordinated group, a cosmic ray ensemble. This hypothesis proposes that multiple lower energy particles could arrive at our detectors in a perfectly synchronized burst, their combined impact mimicking the signature of one ultra-high energy particle like the Oh My God particle. It is a cosmic magic trick, an illusion of energy created by perfect timing. Imagine a single loud gunshot. Now imagine 10 people firing their rifles at the exact same millisecond. To a distant listener, the two sounds might be indistinguishable, a single, powerful blast. A cosmic ray ensemble would work the same way, a perfectly choreographed arrival that tricks our instruments into seeing something far more powerful than what is actually there. This idea could potentially resolve some of the most baffling detections, those events that seem to defy the GZK cutoff. Perhaps these are not lone travelers that have impossibly survived the long journey, but instead a tightly packed group from a much closer source, their individual energies perfectly legal, but their combined effect revolutionary. Finding evidence for this is an immense experimental challenge. It requires searching for the subtlest of correlations across vast detector arrays, looking for patterns that hint at a shared origin and simultaneous arrival. Scientists are developing sophisticated new analysis techniques to sift through the data, hunting for these ghostly squads hidden within the random rain of particles. If proven, the ensemble hypothesis would add a profound new layer of enigma to cosmic ray observations. It would mean the universe's most energetic messages might not be shouted by a single colossal voice, but whispered in perfect unison by a cosmic choir. A brilliant new star blazed into existence in the year 1006, outshining Venus and casting shadows on the Earth for months. Chinese, Arabic, and European astronomers recorded this celestial visitor, a supernova so bright it was visible even in the daytime sky. Today, we know this was not the birth of a star, but its spectacular death, an explosion whose faint, expanding remnant still drifts in the southern constellation of Lupus. This ghostly cloud, known as SN 1006, is more than a cosmic relic. It is a living laboratory, a confirmed factory for the cosmic rays that still wash over our planet. The evidence comes from the high-energy light it emits. When we point our X-ray and gamma-ray telescopes at this remnant, we see a shell of intensely glowing material. This is not just hot gas, it is the telltale signature of synchrotron radiation, the light given off by electrons spiraling at nearly the speed of light through tangled magnetic fields. But the real confirmation arrived with the detection of very high-energy gamma rays. These photons are not produced by electrons, but by protons, the primary component of cosmic rays. The process is a cosmic demolition derby. The expanding shock wave from the ancient supernova acts like a colossal particle accelerator, hurling protons to incredible velocities. When one of these ultra-fast protons collides with a slower-moving proton from the surrounding interstellar gas, the crash can create a neutral pion, a particle that almost instantly decays into a pair of gamma-ray photons. The gamma rays we detect from SN 1006 are the direct fallout from this violent particle traffic jam. They are the flash from the cosmic ray assembly line, proving that the remnant is still actively manufacturing high-energy protons a full millennium after the initial cataclysm. This creates a profound link across time. The same explosion that stunned our ancestors is, right now, responsible for a fraction of the invisible particles passing through your body. A historical event witnessed with the naked eye is permanently etched into the high-energy spectrum of our universe, its legacy written in the language of light and the silent rain of atomic fragments from the sky. High above the Earth, attached to the International Space Station, a silent hunter is meticulously cataloging the universe. The alpha magnetic spectrometer, known as a MS-02, is not just another instrument, it is the most precise cosmic ray detector ever placed in orbit. For over a decade, it has been counting and analyzing billions of particles with an almost unbelievable accuracy, building a map of the cosmic ray flux in unprecedented detail. And within this mountain of pristine data, scientists have found something peculiar, a faint but persistent anomaly that has yet to be explained. It is not a dramatic surge or a single shocking particle, but a subtle distortion in the expected flow of certain cosmic rays. This is not the kind of discovery that makes immediate headlines. Instead, it is a quiet whisper in the data, a hint that the universe might be hiding something just beyond the edge of our current understanding. The international team behind the experiment treats this anomaly with extreme caution. Every potential source of error, from the instrument itself to the complex background of known astrophysics, is scrutinized and tested again and again. The process is slow, methodical, and deliberate, a testament to the painstaking nature of cutting-edge science. The goal is to rule out every conceivable mundane explanation before even whispering the possibility of new physics. So what could this mystery object in the data be? The leading and most thrilling possibility is that we are seeing the indirect signature of dark matter annihilation. The specific energies and types of particles involved in this anomaly could match predictions for how certain dark matter particles would decay or collide. It could be the faint, ghostly signal we have been searching for, finally revealing itself not as a direct flash, but as a statistical ripple in the cosmic sea. Another compelling idea is that the anomaly points to an entirely unknown astrophysical source. Perhaps there is a class of cosmic accelerators we have not yet considered, or a nearby object whose full power we have underestimated. It could be that the complex magnetic fields between the stars are focusing and distorting cosmic rays in a way we have not yet learned to model. Each of these explanations would be revolutionary in its own right, forcing us to redraw our maps of the cosmos. The true nature of this signal remains elusive, a puzzle being worked on by hundreds of brilliant minds. The data from a MS-02 continues to flow, each new particle adding another piece to the puzzle. Is this the first glimpse of a reality beyond our standard model, or simply a deeper layer of complexity in the astrophysics we already know? The answer is hidden within the quiet, persistent hum of the data, waiting for the moment when patience and precision finally reveal the universe's next great secret. These invisible particles may have left their mark not just on the cosmos, but on the very blueprint of life itself. One of the most profound and enduring mysteries of biology is a simple preference, a cosmic quirk known as homochirality. Many molecules can exist in two forms that are mirror images of each other, much like your left and right hands. In the sterile environment of a laboratory, chemical reactions produce equal amounts of both left-handed and right-handed versions of amino acids and sugars. Yet, when we look at all known life on Earth, we find a strict and universal bias. The amino acids that build our proteins are almost exclusively left-handed, while the sugars that form the backbone of our DNA and RNA are exclusively right-handed. This is not a minor detail, it is a fundamental signature of life, and its origin has puzzled scientists for generations. If non-living chemistry shows no preference, why did life make this specific choice? This is where the silent, persistent reign of cosmic rays enters the story with a highly speculative, yet utterly captivating proposal. Cosmic rays are not just energetic, they are polarized. As these charged particles spiral through the galaxy's magnetic fields, their spins can become aligned, meaning they essentially rotate in a preferred direction. This polarization could have acted as a subtle but persistent selector on the early Earth. The hypothesis suggests that as the polarized radiation from cosmic rays interacted with the primordial soup of prebiotic molecules, it may have ever so slightly favored the destruction of one mirror image form over the other. It would have been an incredibly slow and subtle process, a gentle pruning over millions of years. Think of a vast field of seedlings, half leaning slightly left and half leaning slightly right. Now imagine a persistent, gentle breeze that consistently, day after day, puts more stress on the seedlings leaning one way, causing just a few more of them to fail. Over eons, the field would become dominated by the seedlings that leaned with the breeze. In this analogy, the cosmic rays are that gentle, relentless breeze, and the molecules of life are the seedlings. The result would be a chemical environment subtly enriched with left-handed amino acids and right-handed sugars, setting the stage for the first self-replicating molecules to emerge with a built-in universal handedness. Without this uniformity, the complex machinery of life may never have gotten started. Proteins built from a mix of left and right-handed amino acids would not fold correctly, and the precise double helix of DNA would be impossible to form. The cosmic ray hypothesis offers a potential solution to this chicken and egg problem, suggesting an external, astronomical trigger for one of biology's most fundamental rules. Of course, this idea remains at the frontier of science. It is difficult to prove, and other theories, from the influence of circularly polarized light near newborn stars to simple chance, also compete for an explanation. Yet the possibility is staggering. It means the same violent events that tear stars apart and fill the galaxy with invisible shrapnel may have also provided the gentle nudge that guided life into existence. The next time you look at your own hands, consider that their inherent asymmetry, their distinct left and right, might be a permanent echo of the galaxy's own spin, a fossilized record written not in stone, but in the very molecules from which you are made. From the staggering power of a single proton to the subtle asymmetry of life itself, this journey through 25 cosmic enigmas reveals a universe far stranger than we ever imagined. We have encountered particles that defy the very laws of physics, traced faint currents back to stellar corpses, and questioned whether the invisible rain from space could seed clouds or even guide the hand of biology. Each mystery, from the "oh my god" particle to the dark matter whisper in the MS data, is more than a puzzle. It is a boundary, a line in the sand drawn by nature, daring us to cross it. To solve them, we have built detectors the size of small countries and placed precision instruments in the void of space, pushing technology to its absolute limits in a quest to understand the cosmos. These are not just abstract curiosities. They are the fundamental forces that have shaped our galaxy, our planet, and perhaps even our own existence. So we turn the question to you: which of these cosmic riddles captures your imagination? Was it the ancient fury of the Tunguska event, the blurred map of ultra-high-energy hotspots, or the profound possibility that our very molecular structure was influenced by the galaxy? Share your thoughts in the comments below and subscribe to continue exploring the universe's greatest secrets with us.